Hello everyone, welcome to a numerical lecture on digital signal processing. So today's class we are going to see two numericals which will cover all the things that we have seen in this lecture series till now. So what basically we have seen is we have done what is sampling, we have seen what is quantization, and we have also seen what is an oversampling A to D converter. So basically with these numericals today, we will cover most of the sampling theory and the quantization theory. The oversampling A to D problems or the numericals will cover in another lecture. So the first question is, given a continuous signal 3 sine 100 pi t, we are asked to sketch your signal between t equal to 0 to 30 millisecond. Determine the discrete time signal for sampling frequency fs is equal to 300. Compute sample values in one time period ts. And compute your sampling rate for signal to have a peak value of 3. Good. So the first problem has to do with signal plotting or signal drawing, and that is something we have to find the frequency of the signal in order to do that problem. The second sub question is to obtain the DT representation of your signal or the discrete time representation for your signal, which is given by x of n ts, and that is your sampling algorithm. And the third is compute the sample values in one period. So when they ask to find sample values in one time period, they are talking about number of samples per cycle. So we need to find what is the number of samples per cycle. And finally, we have a peak value of 3, and that is an amplitude control problem, right? We need to work with the amplitude of the sinusoid and get the amplitude to a maximum value of 3. What should be done in order to achieve that? So let us see the first sub question. So now we have the time interval given to us is between 0 to 30 millisecond. So which means what I'm going to do is first I'm going to find the frequency of this continuous signal, and that is coming out to be 50, because in 100 pi you have 52 pi's, and that 50 is your frequency of the signal, and frequency is given by the number of cycles per second. So it's 50 divided by 1 second, and now you have 50 cycles in 1 second. The question is, in 30 millisecond, how many cycles do we have? So it is we are solving it as a simple ratio problem, and we are going to get x is equal to 1.5 if we take 30 millisecond as 30 into 10 to the power of minus 3. So which means between the time interval 0 to 30 milliseconds, you have 1.5 cycles. So we can plot this. So that is what the question is, to sketch the signal. So if I am going to plot the signal, I'm going to have 1.5 cycle, which means I'm going to have a full cycle of a positive and a negative. This is my full cycle, and then I'm going to have my another half cycle. So this between 0 to 30 millisecond, this is your 1.5 cycles. So that takes care of the first sub question. So now we can move on to the next sub question B, which is your DT signal computation. So how do you find your discrete time signal from a continuous time signal? So you have been given a continuous time signal xa of t, and how do you obtain the DT signal? So we are going to use the sampling algorithm that we have seen, which says that x of t is equal to x of n ts is equal to x of n by fs. So this is the sampling algorithm that we have seen here, and this sampling algorithm is used in conversion of your continuous to discrete. And now my sinusoidal signal is given by sine 2 pi fn. Good. That is the formula for a discrete time sinusoid, and my sampling is given by x of n by fs. So combining these two into a single quantity, I'm getting sine 2 pi f by fs of n, right? Taking these two into consideration in writing my discrete time sinusoid, I'm writing it as sine 2 pi f by fs of n. So f is my frequency of the signal and fs is my sampling frequency. And in this question, it is given my sampling frequency is 300. So I write that as direct substitutions of f and fs will give me my dt signal. So sub-question C is telling us what are the sample values for one period. So I'm going to do a few things here. I'm going to write what are the nodes, what are the available things from the question. I know the frequency of my signal, which is 50 cycles per second, and I also know my sampling frequency, which is 300 samples per second. And now I'm looking for sample values in one period, that is like how many samples per second. Because when they say you're looking for one time period, that one time period is nothing but your one full cycle of your sinusoid. So my one full cycle of sinusoid is gonna contain how many samples? I can directly write it from this 50 and 30 because I have one unit is cycles per second, another unit is samples per second. If I take 300 over 50, I am going to get my unit as samples per cycle. Good. So this is 300 by 50 and that is going to be your 6 samples. So we can also do it in another way as shown here. So I have 50 cycles in 1 second. One cycle, how many seconds? That is 20 millisecond. And 20 millisecond I have means how many samples I get for my 300 sampling frequency. So I get it as 6 samples in 1 cycle. Good. 300 samples in 1 second. In 20 millisecond, how many samples? That will give me my samples in 1 cycle. So this is not to be confused. We can directly take fs by f. The ratio of fs by f is going to give you samples per cycles. So now I have 6 samples in 1 cycle, which means my 1 cycle of a sinusoid is 2 pi. So I need to take 6 samples in the 2 pi interval, which means my separation between the samples is going to be equal to pi by 3. Yes. So that is the separation between the samples. Now I can just go on to find the 6 values in one time period, that is x of 0 to x of 5. So you can just find by substituting n is equal to 0, 1, 2, 3, 4, 5. Good. So that is how you calculate sample values in one cycle or one period or 1 to pi interval, because when I say one cycle we are talking of from 0 to 2 pi for your sinusoid. Now coming to the subsection D, the last subsection for this question, which is the sampling rate for the amplitude to have a peak value of 3. So this is not a difficult question. So if your signal has to have a peak value of 3, that is your x max, that is your maximum value of your signal need to be 3, and that can only happen when your sinusoid signal is having a 1, right? The value of your sinusoid has to become 1, and the sinusoid will take a value 1 when your frequency is what? So when the ratio has to be pi by 2, because sine pi by 2 or sine 90 is 1. So within bracket I should get pi by 2 t, and that pi by 2 happens only when my fs is 200, right? Because 2 pi into 50 by fs, that is equal to 1 by 2, sorry, pi by 2 only when fs is equal to 200. Just check. Right, 50 upon 200 gives me 1 by 4, and 2 pi by 4 is pi by 2, and sine pi by 2t is nothing but what? So the frequency which will get my peak value of 3 is 200. Good. So that is for that numerical. So now we are going to see a numerical on quantization. So we have seen a numerical on sampling. So we'll do a basic quantization numerical, and then that should clear, that should help you to clear the concepts or the algorithms that you have seen in the theoretical lectures. The question is something like this. You have been given an input signal, which is an additive mixing of sinusoids. So when I say additive mixing, it means it consists of more than one frequency, right? So here I'm having two cos. It is a two additive signal. So two signals are mixed together. That's what it means. And your link is operated. So we are talking about a digital link. So this is like a digital communication problem we are seeing in DSP, but still it's good since it covers both sampling and quantization concepts. So what is the link operating data rate? So the bits per second is nothing but your bit rate, right? Bit rate or data rate. So whenever anything divided by second, that's your rate. So bits per second, bit rate. Baud per second, baud rate. Then what else you have? Sampling rate, samples per second. Except for cycles per second, we don't call it as a cycle rate, we call it as a frequency. So we don't have that for cycles per second, but for everything else, wherever you see divided by second, that becomes your rate. So here 10,000 bits per second is your bit rate, and each input has quantized to 1024 levels, which means your quantization is having 1024 levels, 1024 levels. Good. So these are the three things we have been given. We have been given a continuous time signal, we have been given your bit rate and your quantization level of 1024. Now what is being asked from us is first the sampling frequency, the Nyquist rate, the DT signal, discrete time signal, and your resolution of quantizer. So for your sampling frequency of 10,000 bits per second, you have your quantization levels 1024, right? So now from this 1024, I can compute the number of bits of my quantizer, because 2 to the power of b is equal to L. So that is equal to 1024. So which means my bits is given by log 2 of 1024, that comes around to 10 bits. So which means your quantizer is using 10 bits per sample, right? So when I'm having a 10-bit quantizer, what it means is each sample value in my quantizer is represented using 10 bits. So I'm taking 10 bits per sample. Then I'm having 10,000 bits per second. So now I have to find the sampling frequency, which is samples per second. So I can easily get from bits per second and samples per second, I can get my samples per, so right, this is my bits per second, and my quantizer is using 10 bits per sample. So from these two, how do you get your samples per second? Take the ratio 10,000 by 10. So when you do that, you are going to get your samples per second, which is your sampling frequency, and that is going to be equal to 1000, because the ratio of 10,000 by 10 is 1000 or 1 kilohertz. Good. And what is the folding frequency? Because we are trying to find what is your sampling frequency and then what is your folding frequency. Your folding frequency is going to be half of the sampling frequency. So that's going to be 500 hertz. 1 kilohertz by 2, that is 500 hertz. So these are the bits. So this becomes samples per second, and Fs is equal to 1000 or 1 kilohertz. Now the next question is, the subsection B is your Nyquist rate. And the Nyquist rate for an additive mixing of signals, or where you have multiple signals, is given by Fs greater than 2F max. So here in this case, we have two frequency signals. So let us find the frequencies F1 and F2. And the Nyquist rate is given by Fs is greater than 2F max, or that is your maximum frequency of these two signals. In this case, it's going to be 900. So when I say Fs greater than 2 into 900, I'm going to get it as 1800 or 1.8 kilohertz, which is my Nyquist rate. Good. Always use Fmax when you have multiple frequencies of your given signal. Now the next we are going to see, the subsection C, is the DT signal. What is your DT representation from your continuous signal? So we are going to use the same formula. X of n is equal to x of nts is equal to x of n by fs is equal to xa of t. So this is your sampling algorithm. So we are going to use that formula here, and then we are going to find, we have the sampling frequency now. Sampling frequency is given by 1 kilohertz, and now we have f1 and f2, so we can easily write my dt representation or discrete time signal representation. So using these two, you have cos 2 pi f by fs of n, and now we can write my x of n as cos 2 pi. My first signal frequency is 300 upon 1000, and my second signal frequency is 900 upon 1000. So that is your discrete time signal. So the discrete time signal I'm having is 3 cos 2 pi into 0.3, right? So that's 0.6 pi n plus 2 cos 0.9 pi n, simplified form. Good. So that is your discrete time signal. Coming to our subsection 4 of this question is about quantizer resolution. So what are we going to do to find my quantizer resolution? So we are having, what are the things we are having? We have the number of levels. We have the quantizer is a 10-bit quantizer, and we know that we are looking with a sampling frequency of 300. So what are the things that we need to solve this question? So the overall resolution of your quantizer is given by x max minus x min. So that is your separation between the maximum amplitude and the minimum amplitude. And for level resolutions, you are going to use x max minus x min divided by L minus 1, where L represents your number of levels. So that resolution gives you the separation between the levels. So here the question, the trick is, we don't know what is x max and x min. So x max is my maximum amplitude and x min is my minimum amplitude, both of which are not given in the question, at least not directly. So how do we find what is the maximum value and the minimum value for our signal? So we know this. So we know that for a cosine, we have the maximum at +1 and your minimum value is -1. So which means my xa of t is equal to 3 into 1 plus 2 into 1, because that maximum of cos is +1, and my x max, when the x of t becomes x max, both the cos have to have maximum value, and for the x min, both my cos has to have a minimum value of -1. So which means for x min I'm going to compute, I'm getting -5, and for x max I'm getting +5. Now my level resolution is given by 5 minus 5, this is 10, divided by 1024 minus 1, this is 1023. So that is for today's class. Thank you.